Hello, my students, and welcome. This is Dr. Sirme. For this video, I want to take you through KCSE 2023 Chemistry Paper 1. And I've said this is Dr. Sirme. For KCSE 2023 Paper 1, that is Chemistry Paper 1, you can see the distribution of marks per class. This paper had 10 marks from Form 1 work. It had 17 marks from Form 2, 25 marks from Form 3, and 28 marks from Form 4. Just like I said with the previous paper, that is paper 2, as you can consider, Form 3 and Form 4 work, that is 53. More than half of the paper is for the Form 4s and Form 3s. So as you revise, my student, do not ignore Form 3 and Form 4 work. That is the true chemistry we can talk about here. Okay, we first of all go through the question paper. And this is my norm, my student. I do prefer taking you through the question paper, attempt the question, then we go through the question or the answers together. That was the cover page for the paper 1 for last year, that's 2023. I want you to pay attention to 4 instructions here, my students. I've noted that most students ignore them. Maybe not very many, like for the first one, writing the name, the index number. Some few students do ignore that. Instruction part C, you answer all questions in the spaces provided. I think when I was doing paper 2, I did emphasize that my student is going to use tick to the space that you provided. And then all working must be clearly shown where necessary. So I'm encouraging my student, work on your handwriting, work on your spellings as well. Then a candidate must answer questions in English. Well, I don't know whether your teacher do use another language to explain, but whatever chemistry you have, you should put it in writing in English. This time round, the paper had 27 questions. As you can see, these are short, structured questions covering from Form 1 work all the way to Form 4. Paper 1 is not very easy to predict. It's not like paper 2. This paper, the question can come from any corner. Good. That is question number 1, derived from Form 2 work. Some structure of the atom there. Yes. Go through the question. That's question 1. Question 2, my students. The types of salts there. Some stoichiometry there. And an equation to write. We got question number 3, again from Form 2, salts. Yeah, you can see the thermal decomposition of nitrates. Then my student, to go to question number 4, this is a metal extraction. Go to number 5, my student there. Okay, number 5, question on solubility of a gas. Moving on to question number 6. Yep, that is a question extracted from sulfur and its compounds. That is contact process there, I think. Question number 7, you can see an equilibrium there for you, student. Moving on to a qualitative analysis using ammonia solution and copper 2 ions. Question number 8, molecular formula of an organic compound there. Then moving on, that's organic chemistry. Question number 9, question on water hardness. Yep. Moving on to question number 10, you can see an energy level diagram there for you, my student. Okay. Question number 11. Yep. You can see number 11 there, combining some gases, oxygen, hydrogen, and the like there. That's, I think it's from the Gay-Lussac's law. Okay, we move on to question number 12, polymers there. Question number 13, my student, you can see there, a question on rusting of iron. Then question number 14, some mole concept. Go on to question number 15. As you can see, that is a question on that is what? That is carbon monoxide. Yes. And that is question number 16, my student. Question on mole concept, again some calculations. Then number 17. Number 17 is there. Good. Move on. Number 18. These are alkaline earth metals. Some reactions. They are concept to do with alkaline earth metals. Go on to number 19, my students. Okay, number 19, there it is, electrolysis, or rather it is effect of an electric current on substances. Then number 20, yep, number 20 is there. Radioactivity, yes. Number 21, a question on mole concept, again, titration. Some things to do with titration there. Number 22, you can see back to Form 1 work. The experiment there to determine the percentage of major components of the air. Good. Number 23, you can see number 23 there. Again, back to Form 4, energy changes. Some energy changes there. Number 24, back to Form 2, structure and bonding. Number 25. Some chemical properties of gases there, not chemical actually, this should be physical. The gases are given 3 of them, that is from Form 3 work. Then number 26, you have some processes, you are to identify the compounds. Okay, and part B there. Then number 27, this was the very last question, derived from Form 1 work, that is fractional distillation, and of course the question there. And that was the end of the question paper. So my student, kindly stop the video, attempt the questions. You can as well rewind the video, go through the paper, or rather you can even try to get the physical having gone through the question paper by yourself, now we can go through the marking scheme together. Well, that is question 1. The atomic numbers of nitrogen and fluorine are 7 and 8 respectively. So the student was expected to draw a dot and cross diagram to represent the molecules. If you can see what I have highlighted here, my student, molecules, not atoms, of nitrogen and then fluorine. These are called the Lewis diagrams. All the student needed to do is to identify, or rather write down, the electron arrangement of nitrogen atom 2,5. So like nitrogen is in short of 3 electrons. Okay, so what exactly will happen, because these are non-metallic atoms. So like for me to come up with the nitrogen molecule like this, I need these 2 atoms of nitrogen need to bond covalently. So there will be sharing of electrons, 3 of them here. They will share 3. So each nitrogen atom will donate 3 to be shared. And automatically that will be 3 pairs, 6 of them. Then a lone pair remains outside. So a common mistake here the student may do, some of them may say this is nitrogen atom. So then decide to use dots, all of them. That was a point that denied a majority of students the mark. So it is a dot and a cross, where the dot represent electrons for one atom of nitrogen and crosses for the other. And this is how the molecule of nitrogen was to appear. Remember to count that for nitrogen atom 8, the other nitrogen atom 8 in total. Ignoring the inner energy level with the 2, it had no harm. It is okay. Fluorine 2,7. That implies that is fluorine atom is in it lacks 1 electron. to be stable. That is the outermost energy level. So for that case, a pair of electrons will be shared. Then that will be a pair considered for each. Then 6 electrons outside. So just like I've said with the nitrogen atom, this is how the student was to draw a fluorine molecule. Then assuming the circles and of course draw like this, still the student could score the mark. Part B, with reference to the above diagram, these two, considering these two how they look, then the student was to explain why fluorine is more reactive than nitrogen. Just like I've said, if you consider nitrogen, it has 3 covalent bonds. Fluorine has 1. So this is where the reactivity will be pegged. You can say nitrogen has triple bond, fluorine has a single covalent bond that is weaker. So when fluorine is reacting, you do not require too much energy to break the single bond for the reaction to occur. So, but for nitrogen, you need quite some amount there. So, well, the two parts were not tied, but ordinarily, the student should argue with the diagrams. Having said that, we go to question number 2. Okay, types of salts. We have several types of salts: normal salts, acid salts, and the student was to name another type of salt, that is part A. Remember, this is form 2 work. 4 types of salts: normal salt, acid salt, double salt, basic salt. So either mentioning double salt or basic salt, the student scores 1 mark. That's a free mark, my students, so that one you should not miss. Part B, the student was supposed to describe how you can prepare an acid salt. Mark that it is an acid salt using 1 molar sulfuric acid, 0.1 molar sulfuric acid and 0.1 molar sodium hydroxide. Consider that we need an acid salt, and most likely if this sulfuric acid and sodium, it should be sodium hydrogen sulfate. So we make sure, if for example you're using these two, consider this. This is something to do with the stoichiometry of the equation. The mole ratio is 1:1. 1 mole of sulfuric acid and 1 mole of sodium hydroxide. So if the molality are the same, we need to use equal volumes. And this is where the marking was. The student was to state mix equal volumes of 0.1 molar sulfuric acid and 0.1 molar sodium hydroxide. So you can see, maybe it was a bit tricky there, but in every question that my student you're given, ask yourself, why am I given this? Why am I given the concentration? In one or the other, there is something. There is something that the answer we require from the molality. So for this one, as I've written, the space provided is too big, but you just need to state this one statement, and of course you get the mark. If you consider the molality 1:1 there, coming down here to part Roman 2, writing the equation, it is 1 mole of sulfuric acid and 1 mole of sodium hydroxide. Yes, that one. It's not the normal way of formation of a normal salt. Maybe you may tend to be confused where the student writes sodium sulfate here. It should be sodium hydrogen sulfate. And the equation is just like that. The equation looks like that, my student, and nothing else. The equation, most of the chemical equation, it's either 1 mark or 0 mark, or maybe a half. For example, if you just missed some straight symbols there. Okay, we move to question number 3. Good. The student was supposed to write the formulae. Underline that it is the formulae, not the name, of the product formed when metal nitrates given on the table are strongly heated. Maybe after this slide I can show you some summary of what exactly happened if you heat nitrates. But potassium nitrate, you get potassium nitrite, you can see the formulae, and oxygen gas, half for each. If you heat lead 2 nitrate, my student, you're going to get lead 2 oxide, nitrogen 4 oxide, a brown gas, and oxygen. If you heat silver nitrate, a nitrate of a metal that is at the bottom of the reactivity series, you're going to get the silver metal and nitrogen 4 oxide and oxygen. So for the first 2 here, yes, you get half a mark. For the first 2 here, because there are 3, half a mark. Otherwise, if you write 2, you write 3 here, okay, you get the 1 mark. You write the 3, 1 mark. One thing you should know, characteristics of heating nitrates. Most of them, except ammonium nitrate, there will be production of oxygen. And of course, the cracking sounds. Nitrates, all nitrates will burn, or when heated, they produce the cracking sound. And actually, nitrates, they are used in making of explosives. And that explosion, the sound, comes mostly from the nitrates that are burning. That was like that. Maybe I can take you through question 4, then we come back to the summary of nitrates. Zinc metal can be extracted using or from zinc blend, that is zinc sulfide, through 3 processes: concentration of the ore, roasting of the ore, and reduction of the ore. Get that? Concentration of the ore is where you increase the percentage, the content of the metal of interest or the ore of interest. In other words, we are removing the unwanted, most of the unwanted impurities or waste or things that are not necessary, be it sand, be it any soil, be it any kind of things that is not necessary. That is what we call concentration. Roasting is just burning it to reduce it maybe to an oxide that can easily now be reduced using carbon or carbon 4 oxide, any good reducing agent. Now, the student was supposed to explain how the concentration or how zinc blend is concentrated. Remember, this is a process we call froth flotation. Froth flotation. That one you can review. And this is a descriptive question. The way you start it, it will depend whether you get any other mark. If you have a wrong start, even the examiner will not look at your work. The rest of the stories you write, the examiner will not even look at it. So my student, make sure you start very well. Like in this case, the ore is ground or crushed. Then you add water or oil. You can see the distribution of marks. And then you blow in some air. That's the 3rd half mark. And then you can explain what happens. The ore will float. And of course, all the other impurities will sink at the bottom. Then you skim off the ore. Okay? Just the way you do to a cream of milk. You skim it off and you have your ore. Highly concentrated now with the ore. The equation for what happens when you hit the ore, that is zinc sulfide. So you can see exactly what happens, my student. The rules of writing chemical equation must be well balanced. The chemical symbols, chemical formulas, well written. The state symbols, solid, aqueous, gas, liquid, well indicated. So like for this one, that is how you go about it. For the revision purposes, my student, you can notice that this is an question that we can encounter somewhere in a process called contact process. Because with contact process, we need sulfur 4 oxide. We can get it from a metal ore like zinc sulfur. That is zinc blend. That is that. This is a good summary for you. When you hit the salts that we call nitrates, if you hit the nitrates of the very, very reactive metals, higher in the reactivity series, potassium, sodium nitrate, you're going to get their respective metal nitrites, like you can see, and the oxygen gas. If you hit the nitrates of the moderately reactive metals, from calcium all the way somewhere to copper, these metals, you're going to obtain their respective metal oxides, as you can see. Nitrogen 4 oxide gas, that is a brown gas, and oxygen gas will be produced. Remember, oxygen is colorless. Maybe it will be masked inside the nitrogen 4 oxide, But if you lower a glowing splint, you're going to observe some observation, that is the glowing splint will rekindle. If you hit the nitrates of the metals lower in the reactivity series, my student, you can see what exactly happens, like silver nitrate, mercury nitrate. If you hit them, you're going to obtain their respective metals. Nitrogen 4 oxide gas, yep, you can see nitrogen 4 oxide gas, and then oxygen gas. If you happen to hit the ammonium nitrate, you can see, my student, you obtain nitrogen 1 oxide and water. We move on to question number 5. Question number 5, this is solubility of oxygen. Yeah, solubility of oxygen. And the graph, solubility against temperature. How does solubility of oxygen differ or changes with change in temperature? Part A, the student was supposed to use kinetic theory to explain what exactly happened. Maybe the student, you can just see the graph. If you look at the graph, you can see the solubility is inversely proportional to temperature. Just that. But you are to use the real chemistry. Go deep. Try to understand what is happening in terms of kinetic theory. Anytime, my student, you hear of kinetic theory, you have to talk about kinetic energy somewhere of particles. Particles either gaining kinetic energy or something. So it is the kinetic theory just has to do with the kinetic energy of particles. Okay. So an increase in temperature for the mixture of water makes the molecules, the oxygen molecules, to gain kinetic energy. Remember, the gaseous substance have the particles possessing the highest kinetic energy. So if you increase the temperature of these gases or gaseous molecules, they will tend to fly off. They will tend to escape from the solution. So when you hit the water, actually what exactly happened here? When you hit the water itself desires to become a gas. So what it will do, it will first of all eliminate any gas that is dissolved in it. Okay? Something that at a higher level, my student, will learn, called the vapor pressure. But the question was not even going to that extent. The question here demanded the student to explain why, when the water is hot, it dissolves less oxygen. Just that. So what exactly, my student, you need to do? When the temperature is elevated, the oxygen molecules gain kinetic energy and then they escape from the solution. Hence, the solubility decreases. Increase in temperature, decrease in solubility. Part B, with reference to this figure, the student was to explain how this issue here of high temperature, less oxygen will do water pollution. Yes. And remember, the oxygen dissolved in seawater, it's very important for aquatic animals, or what we call the marine life. So that means when the temperature are increased, for example, with the global warming, the seawater will have less oxygen. Less oxygen means the animals survive or living in water, the plants will be endangered in one way or the other. So less dissolved oxygen in seawater results to death of marine, or what we have called aquatic life, or animals and plants. I think, my student, you can get that. One effect of global warming there. Number 6, my student, you're given a flow chart there. We're starting with sulfur. Sulfur is burnt in presence of air. You get sulfur 4 oxide. Stage 1, you convert sulfur 4 oxide to sulfur 6 oxide. More air, yes, going through stage 2, and you get sulfuric 6 acid. Okay, my student, state the optimum conditions necessary for carrying out as reaction in unit 2. Unit 2, where is unit 2? Yes. Okay, the conversion of sulfur 4 oxide to sulfur 6 oxide. A temperature should be between 450 to 500. Any temperature you quote between these two, you get a mark. A half a mark, that is. If you quote the catalyst, vanadium 5 oxide or vanadium pentoxide, or rather you can use platinum. Remember I did the chemistry of sulfuric acid. You can even tell why do you prefer vanadium 5 oxide than platinum. All those stories, maybe next time that's what they will ask. The pressure should be between 1 and 2 atmosphere. Any mention of 2, you get the whole 1 mark. If you just mention 1, a half a mark. And look at this. You have been told to state conditions. My student, do not go for 1. It is plural. Should be more than 1. Any of these industrial process, most likely when you ask for the optimum condition, my student, it is temperature, pressure, and the catalyst. Name the 3. Once you identify the 3, you're good. And we move on to the next one. Stage 2 take place in 2 steps. Yeah, conversion of sulfur 6 oxide to sulfuric acid. Remember, even in the book, it is 2 of them. What exactly do we do? Sulfur 4 oxide, or sulfur 6 oxide, actually, this sulfur 6 is dissolved in concentrated sulfuric acid to make oleum, or what we call spiral sulfuric acid. Remember the obvious question here, why can't we dissolve it in water directly? You remember that? The reaction is highly exothermic. It makes the mixture to boil, producing mist of acid, which is not very safe. Okay, step number 2, if we have the oleum, then we dissolve it in water. We dilute it and we get concentrated sulfuric 6 acid. A student could have decided to use the equations, and if the student decide to use the equation, they must be well written, well balanced, without any mistake. So the first one, sulfur 6 oxide dissolving in sulfuric acid liquid, you get oleum. Oleum dissolving in water, you get sulfuric 6 acid. Wow, that is a sweet chemistry there. Sweet chemistry, my student. Number 7, you're given an equilibrium there, my student. Ammonia dissolving in water to get ammonium ion and OH negative. With reference to this equilibrium, explain why ammonia is a weak base. Maybe looking at the equilibrium could not help you much, because you cannot even tell which side the equilibrium is inclining. But all that the student was expected to do is to define a weak base. So ammonia is a weak base because it dissociates partially. So if you look at this, if it can go back, then actually by this equilibrium, it can tell you. Now I agree. The presence of the equilibrium here, or reversibility, it tells you ammonia can dissociate partially. It can as well be in its molecular form. Or rather, you can say because the reaction is reversible. Okay, the equilibrium lies more to the left, and that means ammonia, it is more comfortable in molecular form than in ionic form. Or you can say there is less or few of OH ions there, my student, in the solution. That is the meaning of a weak base. Part B, you're given aqueous ammonia and it is added to copper 2 sulfate. First of all, you get the pale blue precipitate. The pale blue precipitate, if you keep adding ammonia, it dissolves to form a deep blue solution. So the student was to write the formulae. The formula of the substance responsible for the blue precipitate. That is copper 2 hydroxide. Remember, I've done this, my student. I've done the quantitative analysis of cations using ammonia in one of my videos. So copper 2 hydroxide, you can see. The deep blue solution, my student, this is a complex that is formed. It is called tetraamine copper 2 ion. That is how you write it. That is the formula. Something you should be very careful, my student, here. Several things. The charge here is 2+, not 2 negative. Some students were omitting the sign or the charge, and that was the end of it. Another thing, it is ammonia, NH3, okay, into bracket and a 4 outside, not ammonium. Maybe this is where most students were making the mistake. by, instead of writing NH3, they write NH4. And learn to write these complex ions, my friend. It will be there. They will bring it in a national exam without any mercy. Number 8, the formula of the molecular formula of 2 straight chain. You remember that? Straight chain hydrocarbon. So not branched. So underline that. Those who may jump into isomers, the structural branched what, you may miss it. Give the general formula of, get this, general formula, not the name. Most of the students were giving the name, but you have been asked to give the formulae of the homologous series for this. How do you go about this? Look at this. This is 4, okay? 4 carbon. How do you talk of 6? This is 4 times 2, 8 minus 2, okay? You can see it's as simple as that. Carbon is N, H, it will be 2N, yes, then subtract 2. As simple as that, my student, and you get the mark. Then go ahead to this one. This is part B. You draw 2 structures of the 2 compounds. Remember, we said they are straight chain, okay? Straight chain. And of course, give their names. My student, when you get this word draw, it is the open structural formula. That one I emphasized even in paper 2. It is the open structural formula. It is an alkyne, so I must see a triple bond somewhere. Yes. And then, of course, remember one thing, my student. All carbon atoms in an organic compound must possess 4 bonds. Get that? 4. So I must do physical counting. 1, 2, 3, 4. 1, 2, 3, 4 all around. 1, 2, 3, 4 all the same. So just like that. And of course the hydrogen, 6 of them. I must see the 6. If I have the first one, this is a but1-ine. Or you call it a butane. Then I have this. I can shift the triple bond to the second carbon. Yes, now it's here. Remember to fix all the carbon atoms with 4 bonds, hydrogen well indicated, without missing any. This is a but2. The double bond is at carbon number 2. Remember, we go for the least number. That is but2-ine, like that. In case, my student, you use a diene, it is acceptable like this one. It is still a straight chain with 1, 2, 3, 4, 5, 6, 6 hydrogen and 4 carbons. This is a but1 and 2 diene. Okay, a friendly marking here. The structure is not necessarily tied to the name, or rather the two are not tied, because you can miss just a bond, but the name is correct. Most of the students forgot it is 4. They were writing 3 carbons, and that was the end of the marks. Number 9, water hardness may be temporary or permanent. You write the ion responsible for temporary water hardness. Remember, water hardness is caused by the presence of carbon, not carbon, the presence of calcium or magnesium ions in water. For temporary water hardness, yes, the water has calcium or magnesium, but this calcium and magnesium is combined with a bicarbonate, or what you call hydrogen carbonate. So this is the ion that distinguishes the permanent water hardness and the temporary water hardness. So this is the ion that is for 1 mark. Then temporary water hardness can be removed by boiling. One disadvantage of using this, remember, once you're doing the boiling, the calcium hydrogen carbonate or the magnesium hydrogen carbonate decomposes to form their respective carbonates, and these carbonates remain in maybe the boilers or whatever gadgets that you're using to contain the hard water. So this leaves some deposit inside the pipes. We call them scale, far, just the way you refer to them. That reduces the conductivity or the efficiency of the boiler. Remember, when these salts are formed inside, they act as insulators that will maybe make the boiler less of a conductor. That means a lot of energy, and even the process of unblocking it's a bit expensive. That's that. So we go to, okay, you can read through what I've written there, my student. State 1 method that can be used to remove permanent water hardness. Precipitation method using sodium carbonate. You add sodium carbonate, washing soda, soda ash, just to precipitate the calcium or magnesium ion. You can use the ion exchange resin, permitted, or any other as I've written down there. My student, you can as well do distillation. Okay, distillation. We move on to question number 10. Good. My student, you're given an energy level diagram. Energy level diagram for the formation of hydrogen fluoride there. Study this one, study it, then we go together to question Roman 1. You just state the enthalpy of formation of hydrogen fluoride. Energy of formation, that is the enthalpy change. Enthalpy change delta H is always given by enthalpy of the product subtract the enthalpy of the reactants. All you need to know is this: final minus initial. My student, get that? Final minus initial. Final energy minus the initial. And for this one, you have even been given the figures. 100, that is the enthalpy of the product, subtract 370. Not 370 minus 100. It is just this, the way I've written down here. And I get negative 270 kilojoules per mole. In case you are not going to write the correct unit, my student, don't write it. Just write negative 270. For this one, the marking was very friendly. Even writing negative 270 without the working, you have the answer and you have the mark. And actually, a half a mark was added for this. The sign must be there, my student. The negative sign must be there. Then the activation energy. What is activation energy? The minimum amount of energy required for a chemical reaction to start, okay, to initiate a chemical reaction. So the reactant must absorb some energy. What does that mean? It is endothermic. Yep, from where the reactants are, the reactants absorbs energy up to the peak. Over the peak, we call it the activated complex, otherwise called these are the activated ions or particles. So having done that, so the activation energy will simply be 414 subtract 370. Yeah, it's 411 subtract 370. The positive sign must be there. That is positive 41 kilojoules per mole. So my student, do not forget the positive must be there. You'll tell me maybe any figure without a sign, we know it's positive. But for this one, this chemistry, learn to indicate it. Yes, somebody malicious can come over here and write negative. Then you'll have it very rough. Number 11. You're given at high temperature, hydrogen and oxygen can combine. Yup, you can see oxygen combining with hydrogen to get water or steam. In this experiment, a mixture of 200 of oxygen and 300 of hydrogen were mixed. Then, of course, forced to react or provided with the necessary condition to react. Over here, my student, we are using a law that was put across by the guy called Gay-Lussac's. So it's called the Gay-Lussac's law of combining gases. So what did the Gay-Lussac's law say? When gases combine, they do so in volumes that bear simple whole number ratios with each other and that of the product. Maybe you're not supposed to state the Gay-Lussac's law, but it is the Gay-Lussac's law that is guiding you to answer the question. Now, determine which gas was in excess and by how much. Yes, which was the limiting reagent and which one was in excess. Let's argue like this, my student. You're given 200 centimeters cubed of oxygen. Let's consider if this 200 was to react, all of it. According to the mole ratio, it's 1 volume, 2 volume. That is 1 volume of oxygen, 2 volume of hydrogen. That means the 200 of oxygen requires a double, 400. That is 400 of hydrogen. And we are given 300. So what does that tell you? It tells you the oxygen must have been in excess. Let's argue with 300. That tells you the 300 centimeters cubed of hydrogen gas must be used, all of it. Okay? And then that requires a half, that is 150 of oxygen. And of course, according to the mole ratio here, because this water is a gas, 1 volume of hydrogen needs 1 volume of steam, and therefore it will be 300. So the gas that was in excess was oxygen. Yes, it is oxygen, half a mark. Then the excess was 200, subtract the 150 that reacted, you get 50. 3 marks there for the student who had studied that. Calculate the volume of water. Underline water. It is not the final mixture, but water. Water, it will be in line with this mole ratio. It will be the same as the hydrogen here. 300, and you put a tick, 1 mark. In other case, you'll be asked to determine the total volume that was obtained for the mixture. Remember, this 50 is also in the mixture. So maybe I could have added 50 if I am required to give the total volume of the gaseous mixture at the end of the reaction. Explain how we could confirm that the product is pure water. Confirmation of pure water. Don't just say it has a constant boiling point, melting point. No. You just state that, determine the boiling point of the water, which will be specifically 100 degrees Celsius at sea level, or at 1 atmosphere. The freezing point is 0 degrees Celsius. You have to state density is 1 gram per centimeters cubed, and the like, my student. Silk and rubber are examples of natural polymer. Give the name of another natural polymer. As many as I've listed: sisal, wool, cotton, cellulose, protein, starch, DNA, gum from trees, wood, etc. All these are examples of natural polymers. Okay, part B of it. One source of silk, my student. There are some worms that produces silk. They're called silkworms. Okay. It is either you knew them or not, because it was the only answer there. Rubber. Remember, rubber can be artificial, can be natural, but they specifically need to know of the natural sources of rubber. Don't just say rubber, but it is rubber tree, or the latex from trees. That was question number 12. We move on with number 13. The chemical formula for rust. My student, there it is. It is hydrated. Remember, it's not the name. This is hydrated iron 3 oxide. The number of water of crystallization ranging from any 1 to 10. It will be okay. Part B of this one, you're given a setup here, my student, figure 4. And with this figure 4, you have a test tube or a boiling tube. In the first setup, nail just enclosed inside the air. Then you have tap water, you close it, nails are there. Then oil in the third one, placed on top of boiled water, the nails inside. A salt solution, nail, and of course, you can see the setup. Then the student was to explain why no rusting occurred in test tube 3. Okay, the water is boiled and there is oil. That's all you need to argue with, my student. Absence of oxygen. Boiled water is without oxygen. Remember what we said earlier, that when you boil water, you're expelling oxygen. So that is a half a mark. And you have to state that it is this boiling, or rather the boiled water is without oxygen for you to get this half. Then you have to do another half, or get another half, by stating that the oil that is placed on top will prevent the re-entry of oxygen. So even after some time, rusting will not occur. In other words, what are we talking about here, my student? The condition necessary for rusting to occur: oxygen and water. Just state, are they present or are they not present? Look at Roman 2. Select the test tube where the rusting occurred, the highest amount of rust was produced, and give a reason. If you look at this question, my student, you have 2 parts, stating the highest, the test tube with the highest rust, amount of rust, and the reason. So even if it's a 1 mark, remember then the the mark will be divided half. So I look at the 4 test tube marked IV 4. That is where the rusting occurred to the highest percentage. The reason for that, my student, the saltness accelerate rusting. Conditions that accelerate rusting: the saltness, that is, or salinity, then high temperature or acidity. You know what will acidity do? Acidity will react with the rust. Remember, rust is a base, it's an oxide. Then it exposes iron again to agents of rusting, then to continue rusting. Saltiness and high temperature, that one I've said. That's a question derived from Form 1, so do not ignore Form 1 work. That is 3 good marks from Form 1. Number 14, my student, question on Avogadro's constant being used there. It's a question derived from mole concept. So you're given the Avogadro's constant, the 6.02 times 10 to the power 23. Determine the number of moles of iron, ions that are present in 2 molar 500 centimeters cubed of calcium nitrate solution. Okay, what was the student supposed to do here? First of all, let's work out the number of moles of calcium nitrate. So for a half a mark, moles of calcium nitrate, whether you have mastered the formula or you argue out that 1,000 centimeters cubed contain 2 moles. So how many moles will be in a 500? So 500 times 2 divided by 1,000, you get 1 mole. So we are working with the number of moles of calcium nitrate in that solution is 1 mole. Okay? Now, let's look at the formula. And that's why it is important, my student, to know how to write the formula. Calcium nitrate. The nitrate ions are 2 of them here. Okay? So the number of moles in 1 mole of calcium nitrate of the respective ions, we have 1 calcium ion and 2 nitrate. So in total we have 3. Okay? So 3 ions times 1 mole, because they were in 1 mole. In other words, what are we talking about here, my student? It's like I'm talking of a dozen cows. And then I'm asked of the number of horns, assuming all the cows have the horns. So it is 2 horns per cow multiplied by the number of cows in a dozen. Okay? 24. So how many horns are there in a dozen cows? 24. This is 1 plus 2, 3. 3 times 1, 3 moles. So 3 moles times the Avogadro's constant. Remember, mole is a counting unit with this number of units. If you multiply, you get that. The distribution of marks, half, as I've given. Remember, another student could have gone direct and calculate in calcium nitrate. After obtaining this 1 mole, in calcium nitrate I have 1 mole of calcium. So 1 mole times the Avogadro's constant. I get the number of calcium ions separately. Then 2 times 2 for nitrates, yes. Nitrates times the Avogadro's constant, I get it separately, then I add. I'll get the same answer. So what do I emphasize here, my student? Think about calcium nitrate. Nitrate is a particle on its own. It's a radical on its own. Calcium on its own. And again, be able to write the correct formulae. That is that calculation there involving mole concept. The electrical conductivity of 2 molar calcium nitrate is higher than 2 molar potassium nitrate. Look at the number of ions. If you consider the formula, again writing the formula of the ions, calcium nitrate, it has 3 ions per mole. Potassium nitrate, 2 ions per mole. So in other words, calcium nitrate has more ions than potassium nitrate. You can also argue with the higher charge in calcium, and potassium has less. So the conductivity is based on the charge or the number of ions. If you're talking about aqueous substances, the number of ions, if there are many, the higher the conductivity. The higher the charge, the higher the conductivity. That is that, my student. We move on to question number 15. Carbon monoxide and methane as examples of are found in the atmosphere. One disadvantage of carbon monoxide, yes, something we call global warming all the time, or rather called greenhouse effect. It also causes acid rain. So what is this exactly called global warming? Emission of too much CO2 into the atmosphere. They form a kind of an insulator or a blanket that prevents the once the sun's heat gets to the ground, they prevent it from maybe radiating back, and that causes the temperature above the earth's surface to increase. That's what we call the global warming. You know the effect of global warming? Go and study that, my student. One source of emission of methane. Methane, we can get it from fractional distillation of crude oil, natural gas itself, the burning of fossil fuel, decomposition of manure, what we call the biogas, or most of organic substances, excretion of animals, cracking of long-chain alkanes. Once you do cracking of long-chain alkanes, you get shorter one, of which methane is the first member of the alkane series. How can we prevent the emission of carbon monoxide into the atmosphere? Remember the issues to do with pollution, my student. These are key, and in most of the standard papers, question on pollution will always be there. So we reduce the use of fossil fuel or burning of wood, charcoal. We can do plant tree. Yes, my student, I hope you've planted a tree this year. So planting of trees, and that means the trees will absorb the carbon monoxide. Then the scrubbing of the gas, instead of allowing the gas to go into the atmosphere, fix the chimney with some alkalis that will react with this gas. We can use green energy, my student. Use electric vehicles like they are now into the market. The use of solar energy, the reduction of emission of the greenhouse gases. So the issue to do with the pollution, my student, I've said very key. Let's pay much attention to that, and we be champions. Yes, the Gen Z should be champions of environmental conservation. Question number 16. You're given 5.7 grams of chloride of D, and you're told in that chloride, remember this is for chloride, it has 4.55 grams of chlorine. Determine the empirical formula. First of all, my student, you need the mass of the two elements, D and chlorine. Chlorine you're given, D you're not. So do the subtraction. By doing the subtraction, my student, you get a half a mark. Then use the masses you given for D and chlorine. The one you have, the relative atomic mass of chlorine is given and that of D is given. As I've done here, you do work out the number of moles for a half a mark. The number of moles will help you get the mole ratio. Divide by the least. Yes, divide by the least, you get the mole ratio 1:3. That means the empirical formula will be 1D and 3 chlorines there, or chlorides. The formula is there, 2 mark. You're given the relative formula mass of the chloride is 267. Determine the molecular mass. As simple as work out the empirical formula mass. Multiply by N, equate to the relative molecular mass, or what you call the molecular formula mass. If that is the case, you work out the value of N. Okay, you're going to get the value of N. Then multiply the empirical formula with that N, and you get the molecular formula. Remember to open the brackets for you to get D2Cl6. And if you don't open the bracket, the box is gone. We move on to question number 17. Question number 17, you're given the BP of ethane, butane, and ethanol. As you can see on that table, by student, that one as it is, the three, give with a reason why the boiling point of butane is higher than that of ethane. Butane has a higher mass. Of course, you can see the molecular mass is high, or it has large molecules, or longer carbon chain, or more atoms for 1 mark. Then it means it has stronger van der Waals forces. In this question, my student, do not mention about covalent. When you're boiling these substances, you are breaking the intermolecular, the forces of attraction between the molecules, not the types of bonds, the bonds between the atoms. You're not breaking that. You're breaking the molecules. These are molecular substances. So do not talk about covalent bonds. The boiling point of ethanol is higher than that of butane. This question is very common and it will be repeated very many times. Ethanol, because of the OH somewhere, there is the presence of the hydrogen bonding. But with butane being just a simple molecule, it does not have the hydrogen bonding. It has just van der Waals forces. So in butane, purely van der Waals forces. In ethanol, the presence of hydrogen bonding that is even stronger than van der Waals forces, though it is also with some van der Waals forces. But go through that answer as it is, my student there. Number 18. You're given 3 alkaline earth metals: calcium, or rather I have written beryllium, magnesium, calcium. What are you supposed to do? They have added these 3 metals into some water, distilled water, with an indicator, phenolphthalein. So state and explain the observation. State and explain. Get that. If it's a 1 mark, half. In setup 1, where you have beryllium, there will be no reaction. Yes, the solution remains colorless. The reason for that, and of course, my student, you're not supposed to say no observable change. Okay, we've said no reaction, half a mark. The solution remains colorless. Okay, for I think that should be a half a mark. Test tube 2, bubbles. Okay, on pink color forms after some time. That means there is a reaction, a very slow one, that occur after some time. The reason for that, magnesium reacts slowly. You have to state slowly with water to form magnesium hydroxide. Magnesium hydroxide is a base, that's why the pink color will just appear. Test tube 3, bubbles or effervescence, and the solution turns pink. That is maybe within a short time, because we've not said a short time after for beryllium. For magnesium is after a short time. This one is even shorter time. The reaction is vigorous there. Good. Number 19. You're given 3 setups, A, B, C. In the first setup, there is hexane, graphite electrodes. The second one, mercury, graphite electrodes, aqueous sulfuric acid there, and graphite electrodes, the setup for electrolysis. Explain why in A the bulb did not light and electrolysis did not take place. 2 things, my student, here: no lighting of the bulb, no electrolysis. Explain both for the 1 mark. Hexane is a non-conductor because it is molecular. That is half. Or rather, you can say hexane is a non-electrolyte and therefore it does not have mobile ions. Either way, okay, do not say it's a poor conductor. Distinguish between a poor conductor, a non-conductor, and such kind. You can say it does not conduct electricity because it lacks ion. Remember, it is a liquid, so you cannot talk of conductor. You cannot talk of conductor. So it is you talk of electrolyte. It's a non-electrolyte. Part B. Bulb lit, or rather it was the bulb light and no electrolysis in this one. So this is mercury. Mercury is a metal. So mercury is a metal. So it will conduct electricity, but the atoms, the metallic atoms, will not be discharged. So there will be no electrolysis, but it will conduct electricity. Just read through what I've written. Part C. In part C, the bulb did light, and electrolysis took place. Okay. Aqueous sulfuric acid is an electrolyte, half a mark, and that means it contains ions that will be discharged. Okay, they will be discharged, or rather it will dissociate into ions. Ions will be discharged, therefore it will decompose and electrolysis will take place. We go to number 20. Carbon 14 is a radioactive atom or isotope. It decays to form isotope of nitrogen and and nitrogen. Yep, you write the equation. You're given the atomic numbers. So write carbon 14, 14 and 6. Why 6? Atomic number. Decomposing to give you nitrogen 14, okay, and 7. Now balance this. 0 between 14 minus 14 is 0. Then 7, you do 6. 6 minus 7. In other words, you want to balance these 6. So what can you subtract from 7 to get 6? It's a negative 1. So a particle with a mass of 0, negative 1 there, it is an electron, a beta particle there. The equation looks like that. Part B. The archaeologists, they use the carbon 14 to calculate the age of some fossils, or the age of organic matter. State what is meant by half-life. In this case, don't even concentrate with carbon 14. Just define what is half-life. The time taken for a quantity of a radioactive material to decay to half the original mass or count, or just the initial number there. With that, you have the half-life. Part B, Roman 2. You're given the half-life of carbon 14 to be 5570 years there. Then calculate the age, T, of a piece of bone that is was found to have 1/16 grams or mass or count of carbon 14. Step by step. My student, you can start from 1. Go to a half. 1/4. 1/8. 1/16. Until you get this. So how many halves do you have? 1, 2, 3, 4. So 4 times T half equals to, remember the T half, that is 4 halves. 4 times the half-life. That is 4 half-lives. 4 times this, you multiply, you get the answer. Because it is 40 halves. Ndio hizo. Just like that. For a student who like working with the formula, the remaining amount will always be given by 0.5 or a half T raised to power T over T half times the initial amount. If you substitute that, my student, like I've done here, you end up with the same time there, 22,280 years. I hope you're together, my student, and we're moving on well. That is question number 21. A long story there, describing a certain titration. Aim is to standardize sodium hydroxide. We use 25 of sodium hydroxide. We are using 0.1 molar HCl, and then phenolphthalein indicator was used. Then the average titer, the average volume of the acid is 21.5. And then the student was supposed to state and explain why each of the following procedure may affect, or how it may affect the titer, or the titer value there. In case the student rinse the conical flask with sodium hydroxide. Remember, sodium hydroxide will be put in the conical flask. So that means some bits of sodium hydroxide will remain there. So if you have more sodium hydroxide inside the conical flask, it means the average titer, the volume of the burette up there, have to increase. As simple as that. So it's good to rinse with it, but still make sure you drain all of it, okay, to minimize on the errors. Part B. If the student refuses or failed to rinse the burette with the solution, the HCl, that you are supposed to put in the burette, what will happen? Remember, now there will be some traces of HCl in the, no, not HCl, you have not rinsed. If you did not rinse with the freshly prepared HCl. Oh yeah, if you are not going to rinse, there will be some little amount of water, distilled water in the burette. And that means the acid you're going to put there will be dilute. If it will be dilute, then the volume of it will increase. Okay. For part C, my student, this is a question even the teachers themselves maybe could not have seen, but we're using phenolphthalein indicator, 2 ml of phenolphthalein indicator. So what will it affect, or how will it affect the volume of the titer? So my student, you should note that phenolphthalein is a weak acid. So if you add more acid in the beaker or in the conical flask, you are in that case you're going to lower the average volume of the acid because you have increased another acid. So that's why we go for drops, my student. That's why we go for drops. Okay, moving on to question number 22. A question derived from Form 1 syllabus there, my student. And you're given a setup 7A, some phosphorus in a petri dish there or a container there. You have a gas jar and some water. Then the student was to complete the second diagram, that is 7B, and then indicate what exactly will be observed after the setup is left to stand for some time. Okay, this phosphorus, when phosphorus is exposed to air, it will do smolder. It will burn spontaneously. And when it is burning, it uses oxygen. So automatically the active part of the air will be consumed and the water will rise up into the gas jar to occupy the space left there, or the vacuum left. So you can see what will happen. The height of the air inside the gas jar will be as I've indicated there. You can use H initial, H final, or whichever letter you want to use there, my student. So the marking is on the diagram, just one mark, but the explanation there, the height of the gas jar above the water level, H1, and when there was no further change, the height is as you have seen there. Explain how the percentages, look at this, plural, of the major components, my student, of the air can be calculated. So we can talk of the active part of the air. It is the H initial, subtract the H final. You get the height that changed here over the H initial and multiply by 100. Then the inactive part of the air, which is mainly nitrogen and some other traces of CO2 and argon. As you can see there, it will be the H, the remaining part of the air there, H final, over the H initial, multiplied by 100. Just that. Question number 23. The heating value, or what they are calling the heat energy value of fuel, is simply the amount of energy produced by 1 gram of that fuel. Then you're supposed to calculate the heating value of hydrogen and ethanol as it is in the table. My student, you can work out the relative formula mass, or the molar mass of hydrogen, 2 times 1. So then the heating value has been given, or not the heating value, this is the enthalpy of combustion of hydrogen. So divided by 2, you get the heating value. That is in grams per kilojoules per gram. Then you have ethanol, my student. You're given the enthalpy of combustion of ethanol. My student, you're expected to work out the molar, what I've called the molar mass of ethanol. The molar mass. Take the enthalpy of combustion divided by the molar mass, and you get that, the heating value there. Good. It's as simple as that, my student. Other than the heating value, one advantage of using hydrogen and ethanol. So hydrogen will produce water when heated. That is a safe liquid, does not pollute the environment. But remember, hydrogen, it's not a very safe source of fuel, because in case it mixes with air, the burning is explosive, or rather it explodes. So it's a fuel that in case you are using it, you should be very careful. Ethanol is a renewable source of energy. Otherwise, it is cheap, it is easy to store, it is easy to transport. Nowadays, I've seen some type of meko, or I can call the meko in the market, called Coco Jiko. The Coco Jiko uses ethanol as a fuel, and maybe it is relatively cheap. It's relatively cheap compared to other sources of fuel that we use. Maybe you can do your research on that, my student. Number 24, you're given 2 structures, L and M. Look at M. That's L. That is mostly the structure of sodium chloride. Okay. The one for M, maybe that one for diamond. In other words, what do I mean, my student? Sometimes when you're tired of studying chemistry, just take those textbooks and study the diagrams. Read go through the pictures. And finally, you'll get something. You'll master something. So this is these are two structures there. The student was supposed to name the type of structure and bonding in each. So with L, the type of structure is giant ionic. The term giant is key. You cannot name the type of structure if, for example, it's a giant and fail to. So we talk of giant ionic, okay, giant molecular. Talk of others, giant metallic. So giant, and with this word giant, what does it mean? It means it is continuous, it is indefinite, okay? It's not a giant of a monster. It is indefinite, it is continuous in all direction, it has no end, it is not a simple. Think the opposite of simple is giant in as far as structure and bonding is concerned. If you know the type of structure, then you know the bonding. The bonding in the structure L is ionic, otherwise called electrovalent. With the M, giant covalent, or giant atomic, or giant molecular, any of the three. The type of bond throughout the structure is covalent. That's why it is called giant covalent. Why giant atomic? Because the particles there are all atoms. Why giant molecular? Because if you have atoms joined with covalent bond, you're making a molecule. But in this case, you're making a very big molecule that is indefinite. Well, the type of particle can also give you the type of structure. If the building blocks are the ions, so that's giant ionic. If it is atom, giant atomic. If it is molecules, giant molecule. Okay, 25. One physical characteristic that can help you identify the three gases. Hydrogen sulfide. This is a gas with characteristic smell of rotten eggs. Just that. Nitrogen 2 oxide. Some people will call it laughing gas or what, I don't know. But the presence of the sweet or pleasant smell, it's what give the student the mark. Otherwise, this is a laughing gas. It gives the person some hysterical moods. Feel like laughing. This is why it's called a laughing gas. This is a laughing gas. Okay, chlorine, the color. Remember the physical properties are either smell, what you see, the color, and the like. So physical properties. So the green-yellow appearance of the gas will tell you the gas is coming out all. You call it green-yellow, yellow-green. It's okay. Question number 26, that is the name of the compound that can be combined to get the compounds under the process called esterification. Esterification, the combination of alkano and an alkanoic acid in presence of few drops of concentrated sulfuric acid and some warming, a process called esterification. The process that leads to production of sweet smelling compounds called esters. So you need an alkanoic acid or like a carboxylic acid and an alkano or alcohol. The two, without necessarily talking of the two like alkanoic and carboxylic, it's either one, alkano or alcohol, but alkano the better. Saponification, the manufacturing or synthesizing of soapy detergent, fats and an alkali like sodium hydroxide and fats. You can say oil, you can say esteric acid, lipids are also types of fats and the like. So a suitable alkali will do there. Importances of vulcanization, hardening of rubber. You harden rubber to make it more useful, like the making of tires, making of anything that is made of rubber that needs a stronger rubber, or just simply manufacture of rubber. Question number 27, you're given that setup there. The intention is to separate two liquid. Liquid Q, boiling point 117. Liquid R, boiling point 103 degrees Celsius. This setup, and that's why I've said, my student, if you're very tired and it is late in the day when you don't feel like studying chemistry, just study the diagrams, and that will help you. The mistake for this one, you look at this, because it was all about identifying the mistake in the setup. The thermometer down here, it is too deep. Actually, it should be at the end of this, or rather the exit of the fractionating column towards the condenser, because that's where we want to measure the exact boiling point of steam coming out. This is another mistake here. Water inlet should be down here, then up here should be the water outlet, just to make the condenser more efficient or effective. Then over here they're using a water bath. In the real sense, they should use some maybe direct heating that will make the temperature of the mixer to go above 117. So you cannot use water bath that heats up to 100 and you intend to achieve a temperature of 117, 103. It is not possible. So I think I've answered the question. 3 mistakes. Thermometer was too deep into the column. It should be up there at the adapter of the to measure the temperature of the vapor. Mistake 2, water bath again cannot help the student or the person doing the experiment to attain a temperature of 117. It should go up to 100. This one. Water inlet, water outlet. They were reversed or interchanged. The opposite should work so that the counter cooling may occur very effectively. That is okay. The container ought to have had that is a column. The fractionating column ought to have had some glass bits, but I tend to think they also had the baffles. But that could have been a point in case the student had no idea of any of the 3 above. Having said that, we are done with the paper, my student. That's the end of the paper. Maybe some few insight here. Look at the theory paper for the KCSE 2023 and paper 1 and 2. If you consider Form 1 work, 2 papers, the theory paper had just 14 marks for the Form 1. Form 2 work, 40 marks, that is 17 and 23. So if you add the 2, that is 54. Okay? Look at the Form 3 and Form 4 work for both papers. Okay? Over here, in this paper, you've seen it is 53. Over here, it was 53 again. So we are talking of 106 marks derived from Form 3 and Form 4 work. So my student, that's where the chemistry is. That's where the elephant is. Mostly the examination of theory paper, in most cases, it will capture Form 3 and Form 4 work. But that does not mean we ignore Form 1 and Form 2 work. Look at the setting. Look at the areas that were examined this year in theory paper. Right from the gas law and the mole concept, the highest marks captured there. Periodicity, that is Form 2 work. That is topic 2, Form 2, topic 1, topic 2, topic 3 there. 21 marks. Organic chemistry will always be there, 20 marks. Electrochemistry, 15 marks. Acid-base indicate, and those are acid-base salts, 13 marks. That is the chemistry or the inorganic chemistry. Chemistry of carbon, 12 marks. Reaction rates and equilibrium, 12 marks. Energy change, 11 marks. Separation of mixture and classification of substances, 8 marks. Those are the area they concentrated. So look at the one I've highlighted in blue here. These are areas that can also be examined. Yep, but last year the working was not well done. They were not well captured. So as you study, my student, try to look at them in detail. And the chemistry of chlorine last year was not even considered. So this year, most likely, if at all, these guys are fair enough. Just stop the video and look at those areas as you look at good ways to revise chemistry, my students. There are too much of the good information online in books, some good books. My students, you can make sure you look at them. Thank you for watching the video. I want to give some special gratitude to some of the people who helped me to come up with this good work. There is a good friend of mine called Mr. Waikwa. Is an ACE, I think, in paper 1. Thank you so much, sir. Your work in one of the seminar was very useful. Mr. Ongai Robert, thank you so much. That's an examiner in paper 1. Thank you so much for guiding me through. Then a good guy who is a chemistry guru called Martin Buguswa. I think I referred to most of your work for this video. And to all my fans in Dr. Sirme YouTube channel, once you watch this, refer it to somebody, and if you have not subscribed, just subscribe, like it, leave your comment there, and I'm sure I'll appreciate. Thank you so much, and God bless you, and God bless you. This is Dr. Sirme. I love you so much, you people, and chemistry is very easy, my student. Make sure you revise hard. We need doctors, we need engineers, we need professionals in the years to come, even as we will come the CBC. Science will not change. Okay? Science will not change. Thank you very much, and thank you very much.